Climate Change and the Three Little Pigs. Once upon a time, there were three little pigs. They studied past climate conditions to protect themselves from various natural dangers and decided to build their own houses. But they all had different thoughts on how to protect themselves from past disasters. The first little pig built a straw house. It was built to emit less CO2 during both construction and operation. However, temperatures gradually rose, and the poor little pig couldn't withstand the heat. The second little pig built a well-ventilated and climate-adapted wooden house. However, it was struck by a massive storm, and the poor little pigs lost their house against disaster one more time. The third little pig built a brick house that was strong and resistant to disasters. The new house was strong enough to withstand storms. Thanks to that, the little pigs had at last found a way to stay safe, and they celebrated all night long. Wait! After some time, living in a brick house led to high CO2 emissions. That CO2 caused temperatures to rise further, and the storms got even more intense than it used to be. Eventually, they began experiencing disasters unlike any they had ever experienced before. They realized that they could not protect themselves by basing their decisions on past experience. As climate change continues to escalate, we have to brace ourselves for unprecedented disasters. Therefore, it is important to predict future changes in the weather and take action based on scientific knowledge, while considering CO2 reduction, adapting to climate change, and measures against disasters. Finally, the three little pigs worked together to build a house while looking toward the future. Guess what happened next? They lived happy forever. Design our future. Takenaka Corporation.
Welcome to today's webinar on long period ground motion in earthquake, a critical topic in the field of earthquake engineering and infrastructure resilience. My name is Sunny from the organizer team of Building Construction Technology, or BCT Expo. I'll be your MC for this session. Welcome all the industry professionals from Thailand and international. We are very excited today to run this webinar in partnership with two experts from Takenaka Corporation and Asia Institute of Technology under the topic of long period ground motion in earthquake, its impact, measures, and effects. First, we'd like to introduce our two distinguished speakers today. The first person is Dr. Pennung, Warnitchai, Professor and Chairman of Structural Engineering Program at Asian Institute of Technology, and he is also a director at Earthquake Research Center of Thailand, and Mr. Junya Sakai, Senior Structural Design Manager, Design Department from Thai Takenaka International. Today, our webinar will cover the following hot topics that could help us understand and gain more insights about the impacts and measures and effects of the long period ground motion in earthquakes. You are now attending the BCT Expo 2025 online webinar via Zoom application. We are conducting this webinar via Zoom. All participants will be muted and cameras will remain off throughout the session. The webinar is being recorded and the copy will be shared on YouTube afterward. If you have any questions, please leave your question in the Q&A box below or in the chat box below. The question will be answered during the Q&A session. Now, let us start by inviting Dr. Pennung to share with us about long period ground motion in earthquake. Dr. Pennung received his doctorate degree from University of Tokyo in Japan in 1990 and have joined structural engineering program at Asian Institute of Technology since 1992. He is supervising master and doctoral students and conducting research studies in the areas of structural dynamics, bridge engineering, earthquake engineering, and wind effects on structures. He was structural engineer at Edcon Company Limited, supervised the construction of the head office building for Ocean Life Insurance Company. He was also construction supervisor at Hitachi Zosen Corporation, oversaw the construction of the Ramanine Bridge project, a cable stay bridge with a main span of 450 meters across the Chao Phraya River. And he was also postdoctoral research fellow at Northwestern University, USA, conduct research on method to reduce vibration in complex structures with closely spaced natural frequency using active vibration control technique. So, without further ado, let us give a very big hand to welcome Dr. Pennung.
Hello, good afternoon. I hope you can hear me well. I'm not sure that you can hear. So someone please let me know that you can hear me well.
I can hear you, yes.
Yes, Dr. Pennung, we can hear you.
Okay. Can I share my slide?
Yes, please. You may share your slide.
Okay. Now I share my slide now. I give a title of my talk about the Bangkok earthquake and what we learned from it. Actually, it's quite related to the theme set up by this webinar. The theme is about long period ground motion. And the recent earthquake in Bangkok, I think everyone can see that it's a kind of long period earthquake ground motion. And it's give an impact to high-rise buildings, which are long period structure. Okay, I'm going to try to explain what we know so far, what we have learned so far about this earthquake. Okay, but the first slide is about Bangkok. You can see that the capital city of Thailand has so many high-rise buildings in the city. Okay, now let's move to the next slide. You can see from this one, the right-hand side picture show seismic activities in this region. Each dot, red dot, black dot, green, blue, each of these is an earthquake event. This shows the activity of earthquake over the past around 100 years. So you can see many earthquake activity in this region, but mostly they happen in Myanmar, in southern part of China, northern part of Laos, Vietnam, and some earthquakes happen in the northern and the western part of Thailand. But you cannot see earthquake or any red dots near Bangkok. Okay, they happen in the north and in the west. All these earthquake activities are tectonic earthquake. It's actually created by the movement of tectonic plate. So most of the movement happen along the crack on tectonic plate we call active fault. So on the left-hand side, you can see many active faults in this region. They are shown in many different colors. The gray color fault represent active fault that are not that active. The rate of activity is low. The rate of slipping is low. We call slip rate is low. They are capable of producing large earthquake, but you have to wait for a long period of time, like several hundred years or 1,000 years, for each of these faults to produce one large earthquake. On the other hand, the green active fault have higher rate of activity. It produces more earthquake. And the red one have a highest rate of activity, is about 10 to 50 millimeter per year. So in this region, you can see one big red fall, and that is Sakai Fall, which is the most active fall in Myanmar. So along this fall, the fall passed through many cities, passed through Mandalay city, passed through Naypyidaw, the capital city of Myanmar. It passed to Pakko and is run close to Yangon, the city, and go down to the sea. Okay, this is the geological condition for this region. About 3.5 months ago, there was a slip along this main fall, the rupture along Sakai Fall. It's not the rupture all along the length, but only some section, starting from Mandalay down to Naypyidaw, okay, several hundred kilometers long. So along this section of the fall that slipped, it released a large amount of energy, produced intense seismic motion. If you watch the news coming from Myanmar, you can see that there were many building damage happening along the fault zone. In this case, the red zone. Because near to the fault that generate earthquake, it create a very strong ground shaking. But when you are getting away from the fault, and the distance from the fault increase, the ground shaking intensity reduce. This is a normal. Okay, so when you are far away from the fault, your ground shaking intensity getting lower and lower. But in this case, something that is not normal happened. When we move down to Bangkok, 1,000 kilometers from the fall, from the earthquake, the ground shaking becomes strong again in Bangkok. Okay, it was not so strong along the past, but it becomes strong again in Bangkok. Okay. Let me show. The main reason why Bangkok have a stronger ground shaking compared to the nearby area is because the geological condition in Bangkok is different. Most earthquake engineers know that the soil condition, the site condition can modify the ground shaking intensity. If the soil or the site condition is a kind of soft soil type, it can amplify the ground shaking. The ground shaking in soft soil condition will generally become stronger than normal. Okay, and inside the country, there is one area that have a extremely soft soil condition. That is the Bangkok and surrounding province. You can see in this map is a red zone. Okay, so it is not just the area with the soft soil. In fact, this red zone is a big soil basin, very deep soil basin. And the top layer of the soil in this basin is a soft soil. But the layer below that are not that soft, but it's kind of very thick soil basin. The depth from the surface down to the bedrock is about 800 meters in the Bangkok area. The basin is very large. The boundary of the basin is Chachoengsao, as you can see here, Nakhon Nayok, Ayutthaya, Samut Songkhram. If the basin actually cover around 14 provinces in this area. Okay. We know that the soil basin, especially deep soil basin, it can amplify the ground motion. And not only it amplify the ground motion, it just amplify only low frequency ground motion. Sometimes we call this low frequency ground motion, we call them long period ground motion, because the low frequency means it takes a longer time to complete one cycle of motion, of oscillation. So low frequency means long period. Okay. So in this case for Bangkok, we studied the basin and we found that the basin itself can amplify the ground motion of many different periods, but most of the period motion that it can amplify, they are all long period. Long period, how long? It's several 1 second, 2 second, or 4 second, or even longer than that. Okay. Different soil basin have a different property. Many basins around the world can amplify long period ground motion, like Mexico City soil basin, Kathmandu soil basin, Osaka soil basin, Bangkok also. But the different basins have a different amplification characteristic. Bangkok has its own property. So we actually study this Bangkok soil basin for many years, and we now know about its dynamic properties. And we know that it can amplify the ground motion many times, at least 3 or more times. It's become stronger, and it amplifies only long period ground motion. The long period ground motion can give an impact to long period structure. The structure on the ground surface, some of them are very tall, like tall buildings. These tall buildings have a long natural period. When the ground motion movement match with the vibration period of this structure, there will be a resonance amplification happen, and it will cause the structure to move more. Let me show you the impact. I think most of you can see this, or some of you may experience directly the effect of long period ground motion. This is an effect to the tall building. On the top, there was a swimming pool, and the water spilled over from the swimming pool down to the ground. These two buildings, they are connecting Sky Bridge, and the bridge was damaged by the different movement of the tall building. You can see this is a SkyTrain mass transit system. It was also shaken by ground motion. And the building that have probably the highest impact is this SAO building, State Auditor Office building, collapsed by the effect of long period ground motion. Now let me explain how long period ground motion give an impact to long period structure. Let me show you 3 examples. The first one is a kind of a tall 50-story building. It has its own natural period, or the period that is like to move. It's about 5 seconds. The second one is a 25-story building with a natural period of about 2.4 seconds. I mean, the period to move in one cycle is about 2.4 seconds. And the third one is about a 10-story building, with the natural period around 1.1 second. So if I move the ground at the period of 5 seconds, which is close to the natural period of the tall building, you can see that the tall building is excited more than other. Okay, this is called resonance effect, when the natural period of the building match with the ground motion movement. But when we change the ground movement to match with the middle one, then this time the mid-height tall building now is shaken more, because of resonance that happened to this building. And when we change the vibration period to 1.1 second, then this time is check the small one. Now, the case of Bangkok, the ground motion is likely to be long, 2 seconds, 3 seconds, 4 seconds. The basin amplify many periods, but most of the amplified periods are long period ground motion, not the short one. So you can see more impact to rather tall structure in Bangkok. Now we know about this problem long time back. And this slide was made many years before the earthquake that just recently happened. We came to a conclusion many years before that Bangkok and surrounding province are at risk of disaster from distant large earthquake because we have a deep soil basin that can amplify long period ground motion. And we have a large number of long period high-rise building structure on top of this basin that will be strongly shaken by the resonant effect with this long period ground motion. We actually predict that there are 3 possible dangerous earthquake scenarios that can produce strong impact to tall building. The first one is the magnitude 7 to 7.5 in Kanchanaburi, around 200 kilometers from Bangkok. This never happened yet, but it may happen in the future. The second possible scenario is earthquake of magnitude 8 along Sakai Fault in Myanmar. So the event 3 months ago was close to this one. The last one is an earthquake of magnitude around 8.5 to 9 along the Arakan subduction zone, which is on the west side of Myanmar. Again, this one has not happened yet, but it happened around 260 years ago. Okay, so we do not know when it will happen again. But all these 3 possible scenarios, we think the chance to have them during our lifetime is very low. It's less than 10%. The chance not to have them during our lifetime is about more than 90%. But it seems that I may be wrong. Okay, it come too soon. But let's see. Since we recognized this problem long time back, we actually introduced the law, ministerial regulation require tall buildings in Bangkok to be designed for earthquake resistance. We require all tall buildings in Bangkok, Nonthaburi, Pathum Thani, Samut Prakan, and Samut Sakhon to be designed against effect of long period ground motion since 2007. Not only having a regulation, but we also have a seismic resistant design standard issued by the Department of Public Works and Town Country Planning, Ministry of Interior. The first version of this standard came out in 2009, and then we revised it again in around 2019. Okay. In this new standard, we divide the Bangkok basin into 10 different zones. And Bangkok itself is a zone 5. And for these 10 different zones, we have 10 different curves we call design spectrum. This design spectrum, actually, the vertical axis show the level of earthquake-induced force in the building. In technical term, it's called spectral acceleration, but basically it's an index telling you how strong is earthquake-induced force in the building. The horizontal axis show the natural period of the building. It's a vibration period of the structure. So the earthquake-induced force depends on the natural period, and it also depends on the location. We have 10 different graphs that will allow engineers to estimate the impact of earthquake in this area. So engineer can design the structure to stand against this impact. So on the 28th March, earthquake happened. This was the strongest that we have ever experienced since. I think we never had this experience before. This is the strongest ever experience since we construct the tall building. So this is we have about 5 seismic stations in Bangkok. This is a record from one station at the King Mongkut Institute of Technology in Thonburi. So it's a Thonburi side of Bangkok. It shows the lateral acceleration horizontal acceleration in north-south direction and in east-west direction. Here is another record in Sirikit Convention Center in the downtown Bangkok. We have several more records available at different locations in Bangkok. The first thing we did after we have this record is to calculate the impact to the building and compare with our design spectrum. Let me show you this one. This slide shows the design spectrum, the level of earthquake that we consider in the building design. The code specifies 2 levels. One is DBE, we call design basis earthquake. Another one is MCE, mean maximum considered earthquake. According to the code, when the engineer design for the intensity of the yellow one, design basis earthquake, buildings are allowed to have some damage, but the damage must be limited to some acceptable level. According to the code, if earthquake at the level MCE happen, the building should not collapse. Okay, this is the target in our standard. We follow the American code, but we modify into our own version. The horizontal axis show the natural period. Let me repeat again. 2-second natural period means the building of around 20 story. 4 seconds mean around 40 story, roughly. 6 mean about 60 story. So the ground motion that we record show the curve around here. Well below the yellow curve, well below the MCE level and DBE level. So when we look at this, it say that the ground motion that happened this time is not stronger than what we anticipate, but although it's quite strong, it's strongest that we have ever experienced so far. But if we follow the standard properly, we conduct a design properly, we should not, building should remain standing, although there may be some damage. The building should not collapse according to this level. So this is preliminary statistics we obtained from Thailand Structural Engineers Association. They sent out many volunteer engineers to conduct the damage survey. And they found that several hundred buildings have damage, mostly to non-structural components, not to structural components. So non-structural components are, for example, partition walls, ceiling, elevator, drainage system, and so on. Okay, but only about 10 buildings have damage to their structural components, like a damage to shear wall, to core wall. Okay, and only one building collapsed, which is a state auditor office. This show example of damage, slight to moderate damage to non-structural components. You can see the cracking on partition walls, plaster, crack. This small crack, but it can, and this is a larger one. I mean, more severe damage that you can see through the wall. Okay, maybe to repair this, you need to knock down the wall and replace it by a new one. These are the damage to non-structural component. Although it does not affect the safety of the building, but it's actually affect the serviceability of the structure. Okay. Now, some building have the damage to the main structure. Like this one is how say, is a hospital building. Rajaviti Hospital building. You can see here, this is a core wall, the reinforced concrete wall. Inside there's a reinforcement steel. You can see the crushing of the concrete and vertical bars, steel bar buckle. Okay, it's buckle. This is a serious damage because it affects the safety of the structure. So whenever we find the damage to the main structure, we stop the use of the building and we will allow the building to be used again after it have been properly repaired. So this is example of the damage to Rajviti Hospital building. This is another example. You can see the damage to the shear wall. Not only on one side, but all around, the wall all around. So this is quite a serious one. Fortunately, this building is still standing. Okay, but you can understand the impact of the long period ground motion to the structure, long period structure. Some of them are serious, some of them are not serious. So in order to understand or get a better picture, we actually use the recorded ground motion that we have in 5 seismic stations in Bangkok to compute one index we call roof drift ratio. Roof drift ratio is defined by the maximum lateral top displacement, we call delta, divided by the height of the building. It's delta divided by h, roof drift ratio. We believe that if the roof drift ratio is high, then the damage in the structure is high. So it's a kind of index to show the impact of earthquake in a simple manner. Okay, now let me show you the calculation of roof drift ratio. This is a result. The picture on the right is computed from one component of ground motion at public work department, north-south direction. The other picture show the roof drift ratio computed from another component of ground motion, east-west ground motion. The vertical axis show the level of roof drift ratio. 0.5, for example, means 0.5%. It means that roof drift is about 0.005. The horizontal axis is showing the natural period of the building. Again, let me repeat again. 2 seconds mean around 20-story building. 4 seconds mean about 40-story building. So you can see that there are many peaks in the roof drift ratio. But you have to know that in Bangkok, there are only not many buildings are having a period longer than 5 seconds. 6, 7, 8, these are represent 60, 70, 80 story building. These are super tall, and we have, I think, just about 10 building. But the building having a natural period around 5, 4, 3, 2, 1, we have more than 1,000 buildings. So most buildings are having a period in a range of 1 to 5 seconds. And in this 1 to 5 seconds, the largest and highest roof lift ratio happen to the building of around 3 seconds. Okay. Some people say that this earthquake is a big test for the tall building in Bangkok. I agree with that idea. But from this result, it shows that they are not getting the same exam level. The building of around 3 seconds, having a natural period of around 3 seconds, have more difficult exam question. I mean, the earthquake give more impact to them. Okay, it produce more deformation in this building. So this building of around 3 seconds are likely to have more damage to non-structural component, more damage to structural component as well. So Rajvithi Hospital building is about 24-25 story. It's just lie in this range. The Immigration Bureau office also have the structural damage, also have the natural period around this range. The state auditor office, that the one that collapsed, also have natural period around this range. So I think the building that have more impact appear to be the building of around close to the peak of this roof lift ratio. There's another factor that I like to explain, which may be linked to the next speaker. That is called the damping ratio. Damping ratio play important role. Let me explain this one. Damping ratio represent the level of ability of the building to dissipate energy, vibration energy. Okay, this animation show 3 buildings of the same size, but have a different level of damping ratio. You can see that if we check all these 3 and let it stop by themselves, the one that have rather high damping ratio, like 5%, will stop first. The one with less damping ratio, 2.5%, will stop later. The one with lowest damping ratio will take more time to stop. Okay, so this gives you an idea of damping ratio. In the past, we used to believe that our building have a rather high damping ratio, about 5%. But based on the study of looking at the code on standard for designing tall building at many countries, it's recommend considering lower damping. So we change our standard to set the damping to 2.5%. But actually, after this event, we have more data, more evidence, and all the evidence seem to indicate that the damping of our tall buildings are lower than 2.5%. They are actually closer to 1%. So why this is important? If we actually check all this building with the different damping ratio, the one with low damping ratio appear to shake more with a stronger movement compared to the one with high damping ratio. So if we come back to the picture, this picture again, you can see that the blue curve actually is for 1% damping ratio, low damping ratio. The red curve and orange curve is for 2.5% damping ratio. The green curve is for 5% damping ratio. But we believe that our structure are somewhere between 1% to 2.5%. Okay, so damping ratio is another factor that influence the response of the building. Not only the natural period, but also the damping ratio. Now I try to set up some idea. You can see the yellow zone, right? The yellow zone is a range of roof drift ratio that you can expect small to moderate damage to your non-structural component. The orange color zone show the level of roof drift ratio that you can expect severe damage to your non-structural component, non-structural wall. Okay, so I think this will give you some rough idea about the extent of damage that we can expect from this long period ground motion. Okay, now let me go through this. This is a roof drift ratio computed from other ground motion. This is from Queen Sirikit Convention Center. You can see that in one direction, it has a peak of around 3 seconds. In other direction, it has a peak of around 4 to 5 seconds. So the ground motion characteristic vary from location to location. This is in Thonburi side. The peak is around 3 seconds. Okay, similar to Public Works Department station. So this show you some idea about the impact of this long period structure, long period ground motion to the structure we have. Now, let me come to the final point. So what will be the future earthquake? Okay, you have seen this case, the case on 3 months ago. It was a large earthquake created by the rupture from Mandalay to Naypyidaw. What we are worried is it may continue to rupture further to the south, okay, in the future. Because after the earthquake rupture, it releases strain energy. It may need some time to accumulate strain again in this portion, Mandalay to Naypyidaw. But the portion below, it may have accumulated some strain energy and now waiting for when the level of strain energy reach some level, then it may rupture again. So in order to understand this, we have to see the history of earthquake rupture along this fault. So let me show you this picture. This picture shows the fault, Sakai fault, and its rupture history. The recent one is a magnitude 7.7 from Mandalay to Naypyidaw. You can see, and the other lines show the rupture in the past. You can see the rupture here in Mandalay. The one before 28 March was in 1912, around 110 years ago, around 113 years ago. Very long time. The portion at Naypyidaw, the past rupture was around 180 years ago. But from Naypyidaw down to Pakko, down to Yangkung, the past rupture was around 95 years ago. So that portion has not been ruptured for quite a long time, but not long enough. We may have to, it may take more time to accumulate more strain, more energy to rupture again in the future. If it's rupture only small section, it may not produce severe earthquake. It may produce 7.1, 7.2, 7.3. Then the earthquake impact to Bangkok may not be so strong. But if it's produced 7.7 again or larger, it may produce even stronger earthquake to Bangkok because it's the same size of earthquake or larger at a closer distance to Bangkok. So this show you the possibility of the future earthquake. But I cannot tell you when it will happen again. Now let me come back to this picture again. When earthquake happen in the future, it may not produce the same ground shaking characteristic again. This time it have a peak at 3 seconds. Next time, the peak may happen at 2 seconds, 4 seconds, depending on the energy coming from the source. Okay. This time, the vibration energy may be more concentrated near around 3 second ground motion. Next time, we may have a different height of the peak. Okay. So how can we prepare ourselves for this one? Okay. But what I want to say is, if you look at the scale, this is about roof lift ratio is less than 1%. If we are able to make our structure more deformable, higher than this level, then our structure will be safe. Now let's look at our structure. This is our structure, tall building. Mostly is made from slab column frame, and we show in the blue color. And the red color zone is reinforced concrete wall or core wall. Okay. Slab column frame are quite deformable, but reinforced concrete wall, it can be brittle if they are not properly designed. If we design our core wall to be more ductile, then our system may be able to deform well. Not 1%, but maybe up to 2%. I don't think I have time to go through, but we have the way to design the core wall. Okay. But this issue have not been properly emphasized in our standard. I think this is one of the issues we need to improve our design standard. The approach is we need to suppress or prevent brittle failure mode in the shear wall. We have, in this event, we have seen some building have a lap splice failure. Some of building have a rebar instability. Some of the building may fail by shear. All these are brittle failure mode that need to be prevented in the core wall. If we prevent all this kind of failure mechanism, then the wall will be more ductile. And from our analysis, we found that if we make the core wall to be ductile, the structure should be able to deform well up to around 2% roof lift ratio if we can suppress the brittle failure mode and we make the shear wall ductile. Now let's come back to this picture again. If we make the shear wall ductile, then our structure should be able to deform up to 2%. Not this level, 0.6, 0.7, 0.8. We can go up to 2%. Then we will not have to worry about the safety of the building. Our structure will be safe, but we may not be able to prevent the damage to non-structural components because, as I showed you earlier, the yellow zone, the orange zone, these are the level. If the structure deform up to that level, the structure will have damage to non-structural components. So how can we prevent the damage to non-structural component? If you want to do that, you need to have, it's shown in this picture, that you need to have extra damping. Because most of the buildings are likely to have damping as low as 1% or somewhere between 1 to 2.5%. But if you increase the level of damping, you can put it down, put the level of roof lift ratio down. Okay? If you want to increase the level of damping, you want to be sure that the structure have high damping level. One way to do that is to install vibration damper into the building. Okay? This is an example of how we can increase the level of damping. I mean, this is an example. One way is to put the viscous damper. But actually there are many ways. There are oil dampers, there are metallic dampers. We can install this kind of device into the tall buildings. And it will increase ability of the building to absorb vibration energy. It will increase the level of damping in the building. Okay. This approach has not been implemented yet in Bangkok. But I think after this event, we may have to seriously consider this option. We may have to consider, this option for the future. It can be also used to improve the performance of existing building. Existing building, if you are not sure about its performance or you want to reduce the risk of this existing building for the future earthquake, you can think about putting this kind of damper into the system. Okay, I think I have spent more time than I should spend. I have a few more slides, but I'm not going to go to that one. I would like to end my talk here. Otherwise, it will take time from other speaker. So let me conclude my talk here. Thank you very much for your kind attention.
Thank you so much, Dr. Pennung, for your sharing on long period ground motion. And we got to learn a lot about the seismic activities that happen in each area, which most of it happen in Myanmar and southern part of China and Laos. We have learned that Bangkok and nearby provinces are soft soil zone and has a deep soil basin, which are at risk of disaster from distant large earthquake. Also, we got to learn about the type of damage that long period ground motion can cause to our building structures, and also how each resonant effect can impact the different size of the building. So thank you once again to Dr. Pennung. Thank you so much. So if you have any questions to Dr. Pennung, please drop the question to the Q&A box. Now, let us welcome Mr. Junya Sakai, Senior Structural Design Manager, Design Department from Takenaka International. He is a seasoned structural engineer with over 15 years of experience in both Japan and Southeast Asia. Mr. Sakai has worked on notable seismic isolation projects across residences and historic wooden structures. Takenaka is a subsidiary of Takenaka Corporation from Japan, specialized in field of building construction and earthquake-resistant devices. The company operates in the field of design and construction in Thailand, delivering a diverse range of projects across industrial facilities, office building, and research development centers, all executed to meet the needs of each project with world-class standards and cutting-edge technology. The company's service highlight is seismic isolation system, the seismic design for building construction to properly resist the earthquake. So now let us welcome Mr. Junya.
Thank you very much. Can you hear me? And I will share my screen. Thank you very much, Dr. Pennung, for the explanation about the long period ground motions. I will share my screen. Maybe you can see my screen, and now I'm going to start the presentations.
Yes, Mr. Junya, we can see your screen.
Thank you.
Please do start.
My presentation is as shown in title, long period ground motion in earthquake, it impacts, measures, and effect. Firstly, let me introduce myself. I'm Junya Sakai, Senior Structure Manager in the Design Department of Takenaka International. 消えない？非表示。Okay. I am Japanese and I born in Osaka, Japan. And until now, I live in 7 countries, mainly in Asia. One exception was at the age of 8 to 11, I lived in Nairobi, Kenya, in East Africa. After graduating university, I entered Takenaka in 1994. And there are 3 roles I experienced written in blue. Firstly, I was a construction site staff to rebuild the school in Kobe after the Great Hanshin Awaji earthquake. There like 2 years. And after that, until now, I'm doing the structural designing. And during that, and 2005 to 7, I had the role of ISO Secretariat of DC98. Developing ISO of basics for design of structures. The country I worked in is indicated in flags here. And to talk about earthquake engineering, I had a seismic isolation project for the wooden temple in Kyoto, in Japan. And also I had experience in Indonesia, office project that the design build of seismic isolation system is adopted. This is a list of contents of my presentation. Firstly, about 5 to 10 minutes of company profile, then about the Myanmar earthquake, and finally goes to the topic of measures for long period ground motion in earthquake. So I'd like to begin with the company profile of Takenaka. In 1610, founder of Takenaka established a business in Nagoya to conduct temple and shrine construction. This is the first style of design and build. In here, you can see the design sketch, and they built based on the design. This was the 17th century, and this design built single responsibility style keep long lasting until now in 21st century. In 1899, the corporation was founded in Kobe, and Takenaka did many challenges for cutting-edge technologies. And in 1974, Takenaka was established, and last year we celebrate 50th anniversary. Takenaka is one of the big 5 contractors in Japan. It is reported approximately 1.6 trillion yen, means 11 billion US dollars in revenues in 2004 fiscal years. And 30.5 thousand employees in our group. The business out of Japan, means the global business portion is around 1/8 of total sales and employees. Somewhat unique aspect of Takenaka is only privately held general contractors among Japan Big 5, and we focus on architecture, less than 10% of civil works, and design build specialist over 70% of project. And we have a trusted partner, so majority of projects are single source awards. Takenaka has 30 offices overseas in Asia, Europe, and United States. In Asia, we have 12 offices, including Singapore, China, Indonesia, Malaysia, Thailand, Vietnam, India, and Myanmar. As I said, Takenaka is design build company, and when we look into design works, Takenaka Design Department is recognized as a leading design group in Japan. Example shown here is the tallest building in Osaka. The height similar to Mahanakon Tower has an attracting facade with multi-functional complex building. And to realize the design and its requirement, Takenaka's construction capability is enough to achieve the quality with sufficient experience. This is an example in Sapporo Dome. This feed of natural lawns goes into the dome at the time of rain and snow. And in the right side, there is a high-rise building condominium connected with 3 layers of sky garden. It was required of high-level construction accuracy in each connecting levels. Just go through with the design build work of high-rise building by photos. Most of the high-rise buildings have vibration control or seismic isolation systems to add value to the buildings. This is overseas high-rise buildings that is not adopted seismic things though. And then move on to back to Japan for the high-rise building with a vibration control or seismic isolations. This is also have a vibration control buildings. And also for the residential, we have a vibration control and seismic isolation of a high-rise building. Takenaka also has a research and development institute in Japan, which is one of the largest construction R&D institute. We have geocentrifuge, wind tunnels, and loading testing machine, and fire furnaces, and so on. There is the project experience shown in photos I passed through. Takenaka is well known in Japan for domes and stadiums, and dome with membranes, a single layer lattice dome, and dome that can open and close, and wooden dome, and so on. They are the stadium in Kaohsiung, Taiwan, in collaboration with Toyo Ito Associates and Ricky Liu Associates. To talk about Takenaka International, we are also the same design and build company, providing the same service as in Japan, Takenaka, as one of the as one-stop solutions. There are 6.2 billion Thai baht of sales amount in 2023. Now the nearly 70%, more than 70% of the client is non-Japanese company. This is the end of the company interactions. Let's move on to the long period ground motion matters. Firstly, as we freshly remain in mind, I'd like to talk about the earthquake in Myanmar. It is already explained by Dr. Pennung, but that is happened in 1:20 in Thailand times on 28th of March, Friday. The epicenter is near the Mandalay, Myanmar, at the depth of 10 kilometers from ground. The magnitude of earthquake is 7.7 mm. So in the below, you can see the photos of the damage of road in Myanmar capital, Naypyidaw. On left side, I'm showing the photos I taken at the office, Takenaka office, located in 26th floor. It has also shaken well. Yeah. 動いた。This is showing what happened after the earthquake. We are evacuating to the ground floor. And this is showing that at the earthquake, people are not that much panicked, comparatively like a bit calm behaviors. Okay. Why in Bangkok far from epicenter, has shaken at high-rise building? It is also related to long period ground motions. The long period ground motion mainly consists of surface waves that propagate near the surface with low attenuations. This is different of the characteristic of body waves, like P waves and S wave, have a distance attenuations. Long period ground motion also amplitude under the condition of thick sedimentary layer above the bedrock of shear velocity of more than 3 km per second. So back to Myanmar earthquake. The epicenter is shallow, and the Bangkok has a thick subsoil layer above the bedrock. It makes a long period ground motion propagate with low attenuation and amplitude by soft layers. That resulted some of the high-rise buildings shown big floor drifts at the top of the buildings, and already shown in Dr. Pennung's slides, the big floor drifts differences between two buildings make a damage to the joint of the connecting corridors. And water in the rooftop pool causes sloshing phenomena and spitted off the water of the buildings. Let me skip. And move on to the next topic. Let us look into the cause in Japan and the actual measures case in Tokyo. This is going to show the videos of tsunamis. That is just the information to one who doesn't know.
Mr. Junya, you need to move the pointer away from the screen.
Oh, I see.
Let's try again. Or could you try to press the enter on the keyboard?
Yes, there is. This is rather not related to the long period ground motion, but it is showing the significance of the earthquakes, the tsunami effect. Okay. So this photo is represent Takata, a beautiful town facing the Pacific Ocean, which is famous for its green trees and white beaches, but it is swallowed up by tsunami like this. At the same time, in Tokyo, where 300 kilometers far from epicenter, this earthquake raised up an issue on the seismic performance of skyscrapers, like in Shinjuku, that now showing in slides. This is also the movies. Enter. This movie is playing rather fast forward though, but showing the shaking of the skyscrapers at that time. This is the same phenomenon we've seen in Bangkok. This is also the videos. This picture shows a slow shaking of some building in Shinjuku areas. We can see the slow movement that corresponded to the first mode of the buildings. The building on the left side is named Shinjuku Nomura Building, that built in 1978. And after this event, Takenaka has retrofitted the building by installing the TMD, tuned mass damper, on its roof. I'll talk later about this in details. Even far from the epicenter, many skyscrapers continued shaking by the Great East Japan Earthquake 2011. This is the same as we seen in Bangkok, and that is due to long period ground motions. Since then, strengthening of the existing skyscrapers has become the key issue in Japan. With a thorough review of analysis and observational record, it has revealed that the damping rate of skyscraper is only 1 to 2% without vibration control systems. A design concept of absorption method is using the plastic deformation of structure members are not desirable because of viewpoint of repairability, difficult to repair. So that the damping systems are necessary, as also in the presentation of Dr. Pennung. These systems are necessary for reducing the damage of the building as well as human fear, especially for long period ground motions. From the viewpoint of resilience, damping systems are applied to most of the recent skyscrapers in Japan. As a mitigation of the risk of long period ground motions, many existing skyscrapers over 200-meter height in Shinjuku, as shown in this slide, are currently retrofitted with additional energy absorption devices such as oil damper, tuned mass damper, and so on. Next, I'd like to introduce the retrofit work that we carried out at the Shinjuku Nomura building, shown in the red frame here to reduce building lateral movement caused by long period earthquake motion and strong winds. Main countermeasure for against long period ground motion are add dampers to install TMD on the rooftop. Damper installation has three disadvantages. Need to be installed on each floor, or construction work is carried out in rental space because this is already used, and external appearance may be affected. On the other hand, TMD installation, fused mass damper installation, can solve these three advantages. So we compared several types of TMD as countermeasure against the ground period ground motions. We had a comparison between the pendulum type and slider type of TMD. The natural period of TMD need to be adjusted to fit the buildings. So the natural period can be adjusted by the length of cables, stiffness of slider, or mass of weight. A slider type only needs to be around half of the height of pendulum types. So we have selected to develop a compact TMD slider type. This is an actual slider type of compact TMD developed by Takenaka. The compact TMD is mainly composed of oil dampers, double-layered laminated rubber bearings, and linear slider guide with single rubber bearings connected to the mass of 700 tons. Slide type TMDs generally use rubber bearings and or linear guides as the mass support systems. Left side shows double-layered laminated rubber bearings. These devices are suitable under small deformations, like in wind load. But in the large deformation, like under big earthquake, this is become like this, and it will be a buckling may occur. In the right side picture shows a linear guide. These devices work from small to large deformations. Devices are stable even under the large deformation earthquake. We've decided to use a mix of these two devices for mass supporting system to combat TMD. The compact TMD is effective against both wind and earthquake load. In case of wind load, horizontal deformation will be small. So this is moving like this. And this linear guide side has a huge gap, so this will not touch to each other. And in case of earthquake load, horizontal deformation will be large like this. So this double rubber bearings comes a little bit sink from here. So the gap is closed and the linear slider will work in operations. So the mass supporting is when in wind load just only supporting by the double layered rubber bearings, but in the earthquake load also the linear slider support the mass. So this is shared loading to two devices. The compact TMD was applied in Shinjuku Nomura building, which was built in 1978, and its height of 203.25 meters. So proposed compact TMD was installed in the machine room on the roof that is limited height of 2.8 meters. It's a free space for the machine room. And client also having trouble with elevator's acceleration sensor reacting by strong wind. And every time that is stopped and cannot be operated. This figure shows a typical floor plan and framing elevations. The typical floor is 51 meter by 33 meters. Structure is steel moment frame with steel plate walls. Steel plate wall is located on the core areas. Prior to actual retrofit work, performance confirmation tests were carried out on the full-size models. We carry out the static test and dynamic free vibration test, two kinds of tests. And the weight of the TMD mass is 700 tons, and the size is 5.62 by 11.8 by height of 1.51 meters. As in left side picture shows double layer laminated rubber bearings. And right side is a picture of single axis linear rail with single layer rubber bearing above. Diameter of both rubber bearings is 600 mm. This picture shows a linear guide slider and oil damper. There is a yellow oil damper can be seen here. This figure shows a tensile load horizontal displacement relationship for x direction with and without oil dampers. In order to confirm the basic characteristic, static tensile test with an amplitude of 100 mm was carried out. Measures rigidity is almost equivalent to design rigidities. The design rigidity is 1.77 and measures rigidity is 1.74 kilonewton per mm. Considering the half of the history width of Q distance within this as friction force and the value of friction coefficient mu against the mass is was confirmed. So with the oil damper is like 1 by 1,000. Without oil damper is 1.4 by 1,000. So there's very less friction, so they can start in function even in the small vibrations, like 1 centimeter by second square. This is also a video. This is a video of a free vibration test in X direction. Okay, so this is showing the video that put in the mass 550 mm, and then it released to see the free vibrations. So the figure shows the free vibration waveform of the horizontal displacement with the time observed during the test in x directions. So at the first time 550 and then release and showing the wave shape like this, and then it is going to make it smaller. This figure shows a relationship between the mass inertia force and horizontal displacement of the two segments, so that at the big segment and small segment. So the hysteresis of segment 1 shows a stable behavior even for the amplitude that exceed allowable displacement of the double layer laminated rubber. The hysteresis in segment 2, rather smaller amplitude, shows linear behavior up to small amplitude. This figure shows the relationship between the vertical displacement by horizontal displacement on the weight. During free vibration, the hysteresis shows approximately the same track. Comes like this, comes like this. So as I said, that if the double rubber bearing has a big movement, will be sunk like 2 millimeters. And after sunk, the linear slider is in operation, so will not go more than this gap. But when we look into the small displacement area in segment 2, we not is the keep the same levels of displacement. This figure shows a relationship between period and amplitude, and between damping factor and amplitude. Evaluate the period and damping constant from pre-vibration waveform in the x and y directions. In both x direction and y direction, and the amplitude increase, the value of cycle also tend to increase. The damping is constant value is 4 to 6%. This building installed a building disaster prevention support system. The monitoring system consists of 3 systems. One is emergency earthquake warning systems, and the building safety assessment support system, and TMD monitoring systems with the displacement meter and accelerometers. Emergency earthquake warning system is predicting the long distance component of earthquake, predicting the behavior of buildings and elevators immediately after an earthquake occurs. Building safety assessment support system has determined the safety of buildings immediately after an earthquake occurs and catch the distribution of maximum acceleration of buildings immediately after an earthquake occurs and catch the distribution of maximum sway angles of buildings immediately after an earthquake occurs. And TMD monitoring system has continuously monitors the motion of the mass damper and confirm the behavior and damping effect of the mass damper after an earthquake occurs. This is the earthquake observation record data on 22nd of November 2016, that is after installed. The earthquake was in Fukushima. The epicenter was offshore of Fukushima Prefecture. So we compare with TMD. This is observed record. And we assume that without TMD by analysis, they calculate from the single mass models with a primary mode. So behavior of with TMD are greatly reduced by the mass damper systems. You can see in this graph. Conclusions. Performance of mass damper system TMD has confirmed by full-size mock-up model test. Mass damper system responds smoothly even for the small buildings movement due to earthquake and wind load. Even in strong wind, the TMD worked effectively and did not suspend elevators operations. Even for the amplitude exceeding the allowable displacement, stable behavior of mass damper system was confirmed. The effectiveness of the mass damper system during an earthquake was confirmed using earthquake records from the building structure monitoring system installed in the buildings. This is the end of my presentation. Thank you for your attention, and see you at the BCT Expo in September. Thank you very much.
Thank you so much, Mr. Junya, for your insightful sharing about the basic of long period ground motion and also the characteristic of each type of long period ground motion. and also the real case of using seismic isolation and vibration control adaptation into different projects. And he also mentioned about the high-tech building disaster prevention system, which we learn a lot from that. And for now, for those who have any questions to Mr. Junya, please drop your question in the Q&A box below. So for now, we are going to the Q&A session. Now, let us read our first question. Are you ready, Mr. Junya and Dr. Pennung?
I'm okay.
Okay.
Okay. Yes.
Now let us see the question from the attendees. Let me open the question for a moment. So the first question is to Dr. Pennung. The question is in English. How did the authorities back almost 100 years ago record the earthquake events with the amount of magnitude or MW? Did we have the seismograph back then? Or let me repeat the question again. How did the authorities back almost 100 years ago record the earthquake events with the amount of magnitude? Did we have the seismograph back then?
No. Actually, we have a seismograph only around 120 years ago. But we can estimate approximate size of earthquake by looking at their impact. And this is the work done by the team from Caltech, Professor Kerry C. and Dr. Wang Yu. This team went to the area and looking at many geological records, looking at historical record, and they estimate the possible rupture zone along this Sakai fault, the time, the date, the length, based on geological, based on historical information. They derive the information from many other sources. So the answer is but today we can estimate this from seismograph data. But in the past, they have to use some other means to estimate. I hope I answered the question.
Thank you so much, Dr. Pennung. And yeah, for the next question is to also Dr. Pennung. What level of damage can be expected from an earthquake with a magnitude of 8 to 9? What level of damage can be expected from an earthquake with a magnitude of 8 to 9?
I cannot see that question from Q&A. Is it in the chat box?
Yes, it's in the Q&A box.
Q&A box.
Sorry, Dr. Pennung. This one because some of the attendees also typed their question in the chat box. So right now, some of the questions are in the Q&A box and also in the chat box. But for this question, is from the chat box.
Can you repeat the question again?
Sure. The question is, what level of damage can be expected from an earthquake with a magnitude of 8 to 9?
Well, I cannot answer this one. You know, the level of ground shaking level in Bangkok depend on not only on earthquake magnitude. It depends also on where it happened or where this earthquake happened. If magnitude 8 or 9 happen at 2,000 kilometers away, then its impact will be very low. If a magnitude 8 or 9 happen at the distance around 200 kilometers away, then impact will be very strong. Okay, so it depends not only on the magnitude of the earthquake, but also the location of the earthquake. So in our seismic hazard evaluation or assessment, we consider both the location of earthquake source, the ability of source to produce the size of earthquake, and also the distance from the source to the site to Bangkok, and also ability of basin to amplify the ground motion. So all these have to be considered together. So basically, I cannot answer that question because I think, as I explained, the size of earthquake, the level of ground shaking intensity depend not only on the magnitude of earthquake, but also depend on where it happened.
Okay, thank you so much, Dr. Pennung. And the third question is also to Dr. Pennung. Will low-rise buildings such as residential houses or low-rise condominiums be affected by long-period earthquake? Should residential house or low-rise condominium should design to be earthquake-proof for deep foundation such as boiler piles or pre-stressed piles? How will earthquake affect their design for the future?
Well, from our seismic hazard assessment, we believe that low-rise building, like a residential house or mid-rise concrete building, about a few story to maybe 7 story, they are not very much affected by this kind of long period ground motion. Okay, so they may not need to be designed for earthquake resistance at all. The structure that need to be designed for earthquake resistance are taller structure, the structure with longer period. So the answer will be that I don't think we should, the typical low-rise or mid-rise building, they may not need to be designed for earthquake resistance. But it's possible that earthquake may cause damage if the structure are exceptional weak, like if they have some extreme weakness in the system, possible that they may be damaged even for very low shaking intensity. So if the structures are designed in a normal standard, have a normal structure, then I don't think they should worry much about the earthquake. What they need to be worried, the structure need to be worried is tall building with a long natural period.
Thank you so much, Dr. Pennung, for your answer. And Mr. Junya, do you also have any opinion regarding this question? Do you want me to repeat the question again?
So sorry about
About this
low-rise
question.
condominium.
Yeah. So
It's
yeah.
the same as Dr. Pennung, so that will not so affected by the long period ground motions.
Okay, thank you so much, Mr. Junya. Now let's move to the fourth question. Now the fourth question from attendee is to Mr. Junya. In Japan, how are buildings retrofitted after experience an earthquake? In case where are the structural elements have undergone plastic deformation, is retrofitting still considered feasible, or is it more appropriate to demolish and reconstruct such buildings? May I repeat the question again? In Japan.
No.
Oh,
Yeah.
okay.
So it is in the elastic, in the plastic deformation means over the elastic range. So it means that element cannot be used that more. So to retrofit the building that faced plastic deformation is a little bit difficult to do. And then I'm not saying to demolish, but this is not a correct structure as in the design condition. So we will think about the other retrofit or way of strengthening for this kind of buildings. So
Okay.
this is this kind of dampers things not be applied to this kind of buildings at least.
Okay, thank you so much, Mr. Junya. Now, the next question is to Dr. Pennung. Normally, the important buildings like hospital must be designed with the amplification importance factor of around 1.5. What do you think about the reason why significant damage occur to the Rajaviti hospital?
I'm not sure about when this hospital was designed and was built, but to me it seems that it have been designed and constructed before we have a seismic regulation for Bangkok. So probably the factor 1.5 important factor was not applied at that time. Maybe the tall building, and maybe at that time, probably they consider only wind load. I'm not sure that I'm right or wrong because I did not check the details of this building. But if they were construct and designed before the time that we have seismic code, then probably that factor doesn't have any impact. But from my experience in Thailand, surprisingly, whenever we check the impact from earthquake in the north, the building that have more damage are schools and hospital. That's quite surprising. But they are supposed to be designed and construct to be stronger than normal building. But in reality, they are weaker and more vulnerable compared to other like a commercial or private buildings. So these are something that we need to look into more details in the future. Yeah.
Thank you so much, Dr. Pennung. Let's move to the next question. Also to Dr. Pennung. Are there any seismic design regulation for non-structural components in the building regulations of Thailand? It is important to control story drift ratio of the structure, but from my viewpoint of protecting people, I think it is equally important that finishing materials such as exterior walls can follow story drift. Do you want me to repeat the question?
No. It's
Okay.
fine.
Sure.
Actually, our seismic design regulation focus on mainly on safety issue, focus mainly on structural elements. But if you look around to the standard in many countries, some countries also have not only structural component, but they also have a design criteria for non-structural component as well. These are something that we can improve our seismic code. And as the one who asked the question, I think the person understand this well. The non-structural component, the damage, some of non-structural components, the damage depends on story drift. The story drift increase or decrease proportional to the roof drift ratio that I show in my slide. Another possible index is a floor acceleration. The floor acceleration also give an impact to some type of non-structural component we call acceleration sensitive. And it's also give more impact to content. The impact damage to content inside the building depend on floor acceleration. So far, this issue have not been focused on in our design standard. But after event, we may have to start thinking about this. Yeah.
Thank you so much, Dr. Pennung, for your kind answer. And for the next question, it's not like asking to any person, but please listen to the question and you can show about your opinion. Maybe we ask both of you. The question is how to find the place, a suitable place to locate the dampers in the building. Dr. Pennung, do you want to answer?
No, I like to hear Mr.
From
Junya
Mr.
Sakai.
Junya. Mr. Junya, do you want to share your opinion?
Well, damper is generally in function when it deforms, moves. So if the first mode is dominant, will be the top of the building will be suitable, I think. Just my opinion. But with the ensure of the analysis, and we can select how the arrangement of the damper will be suitable.
Okay, I can give some comment on that. First, we have to find out what type of vibration mode will be excited by earthquake. In a recent event 3 months ago, most buildings were shaken in the first fundamental sway mode. That's what we have in our data. In a fundamental mode, if we know that we want to suppress fundamental mode, then we design damper to suppress that mode. Fundamental mode in X direction, in Y direction, or north-south direction, or east-west direction. We have to design the structure to suppress those modes, the damper. Now, when you put the damper, normally we have to look for the floor that have high story drift, okay? And then the story drift vary from base to the top. Then we have to put the damper to the story where you have high story drift. But there are many possible story that you can put on. You can just first make the model of the building and then put them on and see whether it works or not. We need to have the computer model of the building. And then we can test our idea. Put this is enough or not enough, how much damping it can be added, that can be done. Okay, I think that's answered the question.
Yeah, I also agree on that.
Thank you so much, Dr. Pennung and Mr. Junya. Now, let us move to the next question. The next question is for Mr. Junya. To Mr. Sakai, what is the standard protocol for residences in buildings under mega earthquake in Japan? Shall we evacuate or stay put while covering our heads under safety triangle?
Yes. I read this Q&A. So firstly, during the earthquake, we have to protect ourselves first. So that is going to the below the tables or protecting the head. That is the first action for earthquake. But after stop the earthquake, to avoid the buildings or the finishing will fall off. So we better go out to the buildings after the shaken has become soft. That is basic things. And also we have to power off the electricity and then cut off the range fire things before evacuations. That is well known in Japan.
Thank you so much, Mr. Junya. Also, the next question is also to Mr. Junya. Can the building structure built by Takenaka withstand earthquake shaking? Let me repeat again. Can the building structure built by Takenaka withstand earthquake shaking?
Yeah, Takenaka, we design based on the Thailand building code that is written in Thai regulation and also Moyopo, DPT. And also we refer to the American codes such as AAC7 and ACIs. So that is the same as other buildings. If there's no special requirement from client, we basically follow that Thailand regulation and code. So that is very. I cannot see where the question.
Sorry, this question is come from another channel, like so
Chat.
it doesn't show in the Q&A box.
But we as we are in the general contractor in Japan and also experience in Japan design, so we will somewhat concerned about seismic in like river arrangement or like that kind of things. But generally, basically, we based on the Thailand regulations on code in designing the structures.
Well, can I add something to this?
Sure, doctor, please.
But normally, the code or standard focus on minimum requirements.
That is a Thai.
Minimum requirements. That mainly, at least we focus on safety. Requirement for serviceability may be not there, or even though we may have, may be quite limited. But these days, there are other options in the design we call performance-based design, where the client can specify what they want to achieve. Not only the safety, but they may also want their non-structural components to remain okay even for long return period earthquake. They can do that if they
Yeah.
adopt performance-based design approach.
Yeah.
But in that case, the client will have to specify and work with the engineers. What they want, spell it out. Engineer may have to explain what are the options for the client. So these are kind of thing I think can be done now and also in the future.
Okay. Regarding the performance-based design, we have already tried to do the same things based on ACI or AC7. But the one difficulty is how to do the analysis, like a time history analysis. What the recorded waves we can use for analysis. That kind of thing is very difficult. So we try to do the artificial seismic wave record based on seismicity with fault position or the location that the building is located. But even though I'd like to have a help of Dr. Pennung how to do the performance-based design based on time history analysis.
Yeah, I understand that.
Later, but this
I
is
think
not the topic of.
the basic issue for performance-based design is you need to have some representative earthquake ground shaking
Yes.
record.
Mm.
And it's difficult to have that. But actually, we have such set of record available. And now we have new record available from the recent event. And we have some estimate future record of future earthquakes as well. So those are available. And actually, our research team are planning to open this up for engineers to use them. So they can go further with a more advanced design up to what they want to do.
Thank you very much. We'd like to catch up the latest information for the Thailand regulations.
Thank you so much, both Mr. Junya Sakai and Dr. Pennung. Thank you so much for very insightful answer. Now, this question is very interesting. Also asking both of you, is seismic isolation system effective for long period earthquake?
For the base seismic isolation system, that is a concept of making the natural period of longer. So that is somewhat not so, sometimes not so effective for long period of earthquake, maybe. So we need to use more both the dampers and the seismic isolation devices to resist with these kind of earthquakes. So not only the seismic isolation is a solution for this long period earthquake.
Yeah,
Dr. Pennung,
actually, seismic isolation, the concept is to shift the natural period from short period to longer period so that it will be separate from the ground shaking period. But now, if we put the tall building on the base isolation, the period will shift to be longer, but the ground motion already long period. So normally, I don't think it's actually my student checked this and they found that it's not so effective. It has some effectiveness,
Yeah, yeah.
but the effectiveness is much lower than normal earthquake ground shaking. The effectiveness is low for long period ground shaking. So it means that it may not worth your effort to put the tall building on isolation system. But if you just and also put the building on the isolation system will cost a lot. But if you put the vibration absorber, it will be more direct and then more effective. But actually, for this aspect, I like to ask Mr. Sakai, is that possible?
Oh, okay.
Yeah, in the recent case, we have, how to say, most of tall buildings sway in the first mode. So one way to suppress them is to put June mass damper to June to the first mode, so that it will add damping to the first mode. June mass damper work because it have to tune the TMD frequency to the building frequency, right?
Yep.
But from our record of two buildings, one is BMA head office, and another is a high-rise building in Sukhumvit area. We found that when the building sway, the vibration period change from one number to longer period. We call period elongation effect. So natural period actually increase around 20, 30, or even 40% of initial value. In such case, I'm just wondering whether June mass damper will still be effective or not. Because the frequency will be offset. Natural period change means frequency shift. So the tuning may not be anymore in best condition. This may happen to concrete buildings. We most building in Bangkok is concrete type, but I think the effect may be less for steel building.
Yeah.
Yeah. So I'm
So,
just
yeah.
wondering whether it will be effective or not.
Okay. Yes.
Thank you so much.
So,
Oh,
sorry.
do you have something more to say?
Yeah,
Please
yeah.
go
The
ahead.
building is steel structure. So that is, I feel like that the elongation of the natural period will be not so big affect to buildings. So that we put the mass dump, tuned mass damper. But for the RC building, yeah, not sure about that. Maybe somewhat the long natural period has been changed under the earthquake durations.
Okay, thank you so much, both Mr. Junya and Dr. Pennung. The next question is, will long period ground motion affect deep foundation in tall building? How do you manage the connection between foundation and main structure?
Actually, what you have to do is to estimate the impact of long period ground motion to the structure, to the building. And then we calculate the maximum load that transfer to the foundation. Maximum shear force transfer to the foundation. Maximum overturning moment transfer to the foundation. If our foundation structure is strong enough to stand against those extreme load, then the foundation should be okay. So our analysis procedure is made in that way already. First, we estimate the ground shaking level. Next, we calculate the structural response, and then we calculate the maximum load transfer to the foundation. And we design our foundation to be strong enough. Then, by that methodology, we should be able to ensure the foundation system. Yeah.
Dear Mr. Junya, do you have any opinion on this?
No, I just agree on Dr. Pennung's answer.
Okay. Thank you so much. The next question we would like to ask Mr. Junya. Is it common
Yes.
to install structural health monitoring to buildings in Japan in order to warn the building residents against building collapse for life safety, result in urgent evacuation during the mega seismic events?
Oh. How I can answer? This building health monitoring system is just for after shaken, what the building frame has changed or like that kind of thing, and also during the earthquake, the behavior will be checked, but it is not used for the trigger of evacuate or action to the residents. Sorry, I cannot understand the intention of questions. Can I see in the Q&A? Is that
Yes,
in the
this
Q&A?
this question is in the Q&A box.
あ、これか。Well, in Japan, there's no system like this.
The
Not
question
yet.
is at the 2:57 p.m.
So it means this monitoring is not for the warning to the residents to evacuate or going to collapse or not like that. We are not thinking about the collapse for buildings, and also that this cannot be with a monitoring system, I think.
Okay, thank you so much,
Is
Mr.
the answer for that? Can be
Thank
the
you so
answer.
much, Mr. Junya, for your question. Dr. Pennung, do you have any comment on this?
Well, actually, my research team is also working on structural health monitoring system. We actually put some vibration sensor to hospital building in Chiang Mai and Chiang Rai, and more recently in Bangkok as well. And the system is designed not to warn the people, but is to monitor the building response, like a vibration. And when we combine with computer model of the building, we can quickly estimate the health condition of the building. We can quickly determine whether the building is safe or not safe. So we will spend only a few minutes to estimate this one. So we can inform the building occupants in the hospital whether they need to evacuate out from the building or they can continue to stay in the building. And this issue can be a serious issue for some building. We think the hospital building is a critical issue because they may have some patient that they call red patient that need a life support system. And to remove them from the top building, tall hospital building to down to the ground is so difficult. But the idea can be used for other type of building as well, not just hospital. And this day, this system become, not so expensive because vibration sensor now, the cost drop down so much. And a system like this is quite inexpensive. So it's easy to have this system this day. Yeah.
Thank you so much. Now, the next question is to Mr. Junya or Miss Dr. Pennung. Given the designing tall buildings to be fully robust against earthquake of magnitudes that could pose a significant risk to the city may be unrealistic, would the incorporation of dampers alone be considered sufficient to ensure structural safety?
I think that
Asking both of you.
First of all, in the design of tall buildings against earthquake, we don't design for any kind of earthquake. We design for expected earthquake that likely to happen from the nearby source or from faraway source. We have to determine all possible scenario, but we don't design for impossible scenario. Okay? So first we have to determine what are possible scenarios. And we determine what is the maximum from that. We design our structure to stand against those possible scenarios. Okay, but in the design, one may assume damping to be low, but one may consider to put damper already. If they consider to put damper in a design process, then they have to put damper in a real building. And they can, once they put the damper, they can assume the structure to have higher damping. Then the design may be easier. Okay? But if they do not plan to put damper, then they cannot assume structure to have high damping. They have to assume the structure to have low damping as it's likely to be. I think that's what I can tell. But you know, in this process, the problem is sometimes we misestimate the earthquake. We think it may be this high, this large from this source, and sometimes earthquakes are larger than what we expected. So there are some, we need to have some margin of safety in the design process. Okay, I think that's all we can say.
Yeah, I agree with that. Because the design is set the condition and then set the criteria and then do the work for that. So if there's no conditions unlimited, we cannot do the design. So we have to set somewhat of the conditions, even though that is a maximum. That is cannot be all considered. So we need to set some conditions before doing the design work.
Thank you so much, both Dr. Pennung and Mr. Junya Sakai. Now we will ask only 3 more questions due to the limit of time, and the questions keep flashing into the Q&A box. So the remaining question, we will answer that through the email later. So I hope that can be helpful for you. So the next question is, following the recent earthquake in Myanmar, is it anticipated that efforts to implement seismic isolation, vibration control, and seismic reinforcement will accelerate in the greater Bangkok area? This one is not in the Q&A box. Yeah, it's in the chat box, Mr. Junya-san. At 3:15 15 p.m. Asking both Dr. Pennung or Mr. Junya, you can share about your opinion. Who would like to take this question?
I'm still trying to understand the question.
Uh,
But it looks like, as I explained earlier, before the event 3 months ago, we actually, the event 3 months ago actually give us many new information. One thing that I realized is the damping of our structure, our tall buildings are much lower than what we anticipate. And then that highlight the effectiveness of adding more damping. It can help reducing the response. So when this become clear, when people understand this one, maybe in the future, there will be more implementation of putting vibration control device into tall building. Okay, but of course, this also depends on the cost effectiveness of the system. If the cost is too high, maybe the developer may not use the approach. But I think the cost, if we design properly, the cost should be within the range of practical implementation. So I believe that in the future we have more. I'm not sure about the second paragraph. I need to study take more time to understand. But I shift the floor to Sakai-san.
I also cannot understand. Sorry.
Never mind, Mr. Junya-san. We can go to the next question. The next question is, do the fault nearby Thailand can produce short ground motion that can impact to low medium rise building in Bangkok area? This one is in the Q&A box. 7 p.m. Do the fault nearby Thailand can produce short ground motion that can impact to low medium rise building in Bangkok area?
I think as I explained earlier, there are another possible case of the fault line in Kanchanaburi that may give an impact to Bangkok City. And for such case, as we estimate, the ground, there will be more impact to shorter period structure, but still in the wrong range. Okay, not 1 second or below, but in a range of 1 second, 2 second, 3 second, that range. Okay, more impact to that range, less impact to 4, 5, 6 second or higher. So the impact from Kanchanaburi active fault will be more on shorter range, shorter period range, but still they are quite long, 1 second, 2 second, 3 second. But the earthquake on, I'll say, Arakan subduction zone will give a more impact to longer period range, like 3 second, 4 second, 5 second or longer. Okay, so there are kind of different zone of impact, but all of these are covered by our design spectrum. So if the engineer design for the specified design spectrum, it should cover all the case.
Okay, thank you so much, Dr. Pennung, for your answer, and also Mr. Junya-san. Now, the last question is to Mr. Junya-san. refer to Japan code is control resonance time not exceed than 3 seconds? That's the question.
I'm not sure with resonance.
Yeah, refer to Japan code is control resonance time not exceed 3 seconds.
どこ行った？Resonance time out exceeds. At least that code is not written about the resonance.
I think the question is not clear.
Dr. Pennung, please help me.
No, I cannot help. The question is not clear. Yeah.
This
I
question
don't
is
think I can
asked
help.
by Mr.
That
Prof.
will be the answer.
Do you want to add anything to the question or clarify the question? Or otherwise, we will change to another question.
Yeah, better, yes.
So let us change to another question that is more clear for our speaker. So the question is, does having a swimming pool on the rooftop help to reduce the effects of an earthquake like the one used in Taipei 101? This one is in a Q&A box, 3:34 p.m.
The sloshing period. Maybe Dr. Pennung. Maybe more.
Okay.
Appropriate.
Actually, the June mass damper sometimes may have a liquid form. We can use sloshing water to make it like a June mass damper. But that you need two factors. One, you have to tune the sloshing frequency to match with the building vibration frequency. I think this is possible. But you need a second factor. The sloshing water should have high damping as well. But in a swimming pool, the damping of the sloshing mode is very low. They need, as shown by Mr. Sakai-san, June mass damper need to have damping ratio around 6-7%, right? Damping ratio. So for June mass damper to work, but I believe that sloshing of the swimming pool have damping less than 1%.
No.
So I don't think it will work at all. So you don't have any benefit of having swimming pool on the top rooftop to work like a June mass damper. You don't have. Only you have other benefit. You have swimming pool on the top, people can enjoy. But if the people in the swimming pool during that time, they can be going slosh with the water, which is quite dangerous. Yeah.
Yeah. That's the answer. Yes.
Mr. Junya, you have any view on this?
Yeah, if like a pool can consider as a mass and then like a pendulum is somewhat will be effective, but yeah, that is not so working, I think.
All right. Thank you so much, both of our speakers. And thank you so much for your insightful answer to all the questions. Now, the remaining questions that haven't been answered, we will send this to our two speakers and then we'll have them answer and then send back to your emails. So as we conclude, I would like to thank Mr. Junya Sakai, Senior Structural Design Manager, Design Department from Thai Takenaka International, and Dr. Pennung Warnitchai, Professor of Chairman of Structural Engineering Program at Asian Institute of Technology, and he is also Director of Earthquake Research Center of Thailand. BCT Expo 주사짐 워代表してタイ竹中インターナショナルには BCT Expo にご支援とご参加に心より感謝も お願いします。建設業界のイノベーションを進めるという私たちの目的にも大きく貢献してくださいました。今後も御社との良い関係が続くことを願っております。改めてありがとうございました。
ありがとうございます。
Now, we would like to ask all of our attendees to submit your feedback of this seminar. Your feedback is very important to us. Now, please take a moment to scan the QR code or click the link in the chat to complete the survey. Last but not least, let me give you a brief interview of BCT Expo. As an exhibition is effective marketing and sales channel that create business, network, and sales deal, you will also have the opportunity to get an overview of building construction technology or BCT highlight, which could be your next useful marketing and sales platform to enter Thailand or Asian construction market. This year, BCT Expo 2025 will emphasize the critical themes of sustainability and mining, aligning with our commitment to driving innovation and environmental responsibility in the industry. Under the concept Building a Sustainable Future in Mining and Construction, the event will serve as a platform for exploring cutting-edge solutions, technologies, and best practice. It aims to connect key players in construction and mining, fostering collaboration to build a more sustainable and resilient future. So, guys, don't miss out on staying updated with BCT Expo. You can now register to attend the event for free by scanning the QR code displayed on your screen and be the first to receive the latest news, event highlights, and exclusive updates about BCT Expo. Now, join us and be part of the movement shaping the future of construction and mining. You can stay updated on BCT Expo news and activities through the channels displayed on the screen, including our website, Line, Official, Facebook, LinkedIn, and YouTube by searching for Building Construction Technology or BCT Expo. Finally, mark your calendar for September 3 to 5, 2025 for the BCT Expo 2025. And we look forward to welcoming all of you from Thailand, from international, from any countries of the world. And see you in Bangkok, Thailand. Have a great day. ขอบคุณครับ